Uh, Welcome everyone, and so it's a pleasure to have Kostas Fokianos with us. Thanks a lot for accepting our invitation.
Thank you.
And so he will. So this is just for the audience. This will be recorded, and please, you can ask your questions during the, either like we can unmute you, or you can post your question in the chat. So Kostas will present auto-distance covariance function for time series analysis. Thank you very much again, Kostas, and the floor is yours. Thank you.
Thank you. Thank you very much for the invitation. Today I will talk about some work that has been done actually, and it's related to this distance covariance function for time series analysis. So I will go over some things that maybe they are known or they are less known. We will see. And then I will finish with some work, some recent work that we did. So I will talk about the distance covariance function and the multivariate distance covariance function. And then I will discuss non-parametric clustering of time series data based on this concept of distance covariance function. So this is the first two parts are a joint work with a student of mine. She graduated some time ago, and the other part is a more recent work with Richard Davis and Leon Fernandez. So let's talk about the distance covariance function. So let's give some generalities first. We assume that x and y are random variables. They can live in Rp and Rq. Then we can consider the joint characteristic function. This is it, f of uv. And then the marginal characteristic function. So the idea is to get to try to measure the dependence between x and y by taking the difference between the joint characteristic function minus the product of the marginals. So because of course you have this u and v, you can also integrate with respect to something with w, let's say. So you take a distance between the joint characteristic and the product of the marginals, and w is a suitable measure that we will discuss in detail. For example, w can be the cumulative CDF of a two-dimensional, let's say, of a p plus p dimensional normal. There's no problem with this. Standard, I mean, you can do this kind of things here. So you can simulate this kind of integral, but we will see that a very particular case of W makes this integral to have a closed form solution. And this is very convenient, as we all understand. So why do we want to consider this distance? Because if it is zero, then the x and y are independent. And if x and y are independent, then this distance is zero. So this is very convenient and can be used to identify relations between x and y, even non-linear relation, because this is the problem, as we all know, that the correlation coefficient usually measures linear relationship. So you can normalize this with a distance variance here, and then you can define the correlation function. So this is it's a straightforward definition. So there is some history about this. So many years, I mean, Farweger, back in '93, considered the univariate case, and he employed this non-integrable function. And he replaced these sample points by normal score quantities. So Sekeli, Rizzo, and Bakirov actually applied this weight function in p dimensions, in q dimensions. These are some normalizing constants. And the thing is that with this function, which has a singularity at zero, as you see, because this u and v, this is the measure of the p, the Euclidean norm of u and the Euclidean norm of v. This singularity creates very interesting things, okay? And one of these is that this choice results to a scale and rotation invariant distance correlation function. So the literature on this topic keeps growing. There are around by December 2023, I found around 2,600 citations. So people are interested in this and they have done a lot of work. So there is work on time series. I mean, we are interested in, to describe time series. So actually there is some early work by Hong, which suggested a similar measure of dependence for testing the IID hypothesis. Remillard, back in 2009, in the discussion part of this paper, proposed the extension of distance covariance to the case of time series. And Zhu actually extended the definition to the case of multivariate still stationary time series. So what we did back in 2017 and 2018, we actually proposed a new univariate test for serial independence when the number of lags increases. And also we generalized this thing to multivariate time series. Even though Zhu has done this for multivariate time series, we actually take a different point of view and we define a matrix onto distance covariance function, as I will explain next. And then more recent work is by Davis, Matsui, Mikos, and Wan, where they actually consider W to be integrable and non-integrable, and they have give many asymptotic results based on this. And so let's understand it a little bit better. How should we apply it in time series analysis? Let's consider the univariate data, then the joint characteristic of, I want to find the joint characteristic of xt and xt plus j. So as you see, it's kind of correlation function, covariance, autocovariance function. I take the joint, then I take the marginal, and then because of stationarity, the joint minus the marginals is like an autocovariance function. It's just the covariance, the autocovariance actually between this transformation EUXT and TVXT plus J. So this will depend on J, and then I can choose here the W I want. So we will choose, of course, this Sekeli and Richo W. So in general, we can see that this is a positive, but xt and xt plus j are independent if and only if this quantity is zero. And then similarly, you can define the auto-distance correlation function by taking the autocovariance function divided by, let's say, the distance variance function. So this is very well defined. It exists because we deal with characteristic functions. There is no any surprises. We just need to find a way to estimate it and to see what it's doing. So actually, you can estimate this in a closed form expression, and you can take now the lag, the pairs xt plus j, and you can define this Euclidean distance matrix. So what you take so this is univariate. Let's think about univariate first, univariate observations first. So this is just the differences at time t and s in absolute value, the distance between xt and x. So this has two indices, and you center with respect to S, you center with respect to T, and then you center all together. You take the ground mean, right? The ground mean. So you just center this ATS in this way by the capital ATS, and then you can define beta T, BTS, capital BTS, in terms of XT plus J. So you can do this. And then this is the estimator for J positive. So you have a closed form expression, and you can also define it for negative values because of the properties of the autocovariance. So this is the of the stationarity. So it's very easy. We just need to define a distance matrix, and we need to center across rows, across columns, and then to take the ground mean of the observations. And we have the estimator. So let's see what does this estimator give that the correlation coefficient or the usual autocorrelation function, the sample autocorrelation function, doesn't give us. So let's examine the performance of the sample autocorrelation function and the sample auto-distance correlation function. So I will use two different models. The one is the ARCH2 model. So it is well known that the ARCH2 model, the observations, the XT, are uncorrelated. So the autocorrelation function doesn't give you any idea about the dependence structure. And I will use also a nonlinear moving average model given by this. This is also uncorrelated sequence. I mean, epsilon t here is an IID normal 0, 1, but it can be anything. Doesn't really matter as long as the mean is 0. And here, this is an example of another uncorrelated sequence, but clearly there is dependence at lag 2, right? There is a dependence at lag 2 because this depends on t minus 1 and t minus 2. So there is dependence, but the correlation function does not discover it because it is employed to discover linear relationships. These are nonlinear models. Now, usually when we use R to do this sample autocorrelation plot, we also get some kind of a straight line. We get a confidence interval, so we can judge about the order of the model and so on. So we will find also critical values. But we need to do it through simulation here. And this is based on wild bootstrap. So this is the autocorrelation function of X. So you see here the sample autocorrelation function. And we have 2,000 observations. Okay, so we generated from the models as I showed you before. So we have a very long realization. So we have here the sample autocorrelation function of X. You see there is no any relation. We don't find any kind of lag relation. And for the X square, we get the relation that we want. Okay? We get that the sample autocorrelation here exceeds the blue lines. This is the distance correlation function for X and X square. So for this for the process X and this for the process X square. So you see this discovers exactly what we want. And this is the important thing. We understand that X is dependent sequence. So you see these are the blue dots here. It's like a confidence interval, but these are simulated confidence interval. This is based on asymptotic normality. And here is the distance correlation function for X squared. So again, we see that we get these lines here that they exceed the blue lines. So it means that there is dependence among the observations. So this is the second example of the nonlinear moving average. And again, this is 2,000 observations. We have critical values at 95% level. So as you see here again, the sample autocorrelation function does not discover anything, but the auto distance covariance function finds this dependence at lag 2. So here are two examples of nonlinear time series where actually the auto distance covariance function can be quite useful and can help us, to discover dependencies. So if XT is strictly stationary and alpha mixing, so alpha mixing, many models are alpha mixing, like AR models, nonlinear AR models, Markov chains, GATS models, okay, under suitable conditions, of course, then it's a consistent estimator. And if this is different than 0, then it's also asymptotic normal. But if this is not, if this is 0, then we have a convergence to a mixture of chi-square process, infinite chi-square process, chi-square random variables, because this is like a degenerate V statistic when this happens. So this is for the univariate. For the univariate situation, this is the results. You see here there is a difference in the rate of convergence. Let's see the multivariate. So we have now a d-dimensional strictly stationary ergodic time series. Suppose that we are given a very good situation. So the covariance matrix, the autocovariance matrix is given by this. We all know this, and the autocorrelation matrix is given by this. Okay, so these are the elements So why not define the same thing, in terms of distance covariance function? That's the idea. But how should we use it? So for a univariate time series, we know that we can do Portman-to test statistics based on Box-Pierce test statistic, the Ljung-Box test statistic, and we check the hypothesis that the first P of this Rj equals 0. For a multivariate time series, the same is true. There is a multivariate Ljung-Box. So it's given by this expression here. And where hats, of course, are the estimators, the estimate of the autocovariance matrices. But these tests are inconsistent for dependent and uncorrelated process. And this has been documented very well in the literature. And the number of lags introduced in the construction of such tests is held constant. But this might not be practical, okay? Because the actual dependence might be of higher order. And they do not detect dependence for nonlinear and non-Gaussian models. This is the case that we are doing here. So actually, we have given a review paper back in 2009, a range of alternative tools for this kind of problem. So the idea is to define the matrix value auto-distance covariance function. So you take the R component of the series and the M component at t plus j, at time t plus j. And then you take the joint. And so the covariance between this and this is the join minus the product of the marginals, right? Because of stationarity. So this is the FR is the marginal characteristic of XTR, and FM is the marginal characteristic of the M series. So we get two series at different times, and we find the distance covariance function between them. We find this quantity, and then naturally we can integrate. These are univariate now, and we can take the pairwise auto-distance covariance function based on this. And also we can define the auto distance. So then we can collect on this, and we can have a d by d matrix, and we can have the auto distance covariance matrix. So of R and M time series. So if J is different than 0, VRMJ is different than VMRJ because they measure different dependent structure. Okay, the one measures this to this, and the other measures the XTM to XT plus JR. So it's a different dependent structure. So similarly, we can define the pairwise auto-distance correlation function between XTR and XT plus JM. So it's the positive square root of this guy. So I just do the usual normalization with the variance or distance variance. And then I can collect all this, and I have a d by d matrix again. Now, can we interpret something about this matrix? Well, first of all, the off-diagonal elements at lag 0 measure the concurrent dependence between XTR and XTN. If you can think about it, if you put here j equals 0, then we measure the dependence between XTR and XTM. So we measure the concurrent dependence between these two components. If this is positive, then they are concurrently dependent. Now, VRMJ, if J is not 0, measures the dependence between these two components. If this is 0 for all J positive, but VMRJ is greater than 0 for some J, then we can conclude that XTM does not depend on the past values of XTR, but XTR depends on some past values of XTM. And if this is 0 for all J, then these two are independent. So you can do you can say a few more things, about interpretation, but it's a clear interpretation that we can actually talk. We can interpret this matrix the same way we interpret the autocorrelation matrix or the autocovariance matrix. Estimation proceeds as in the univariate case. Large sample properties of the estimators are given in this work with my student. We have also simultaneous confidence interval for testing the IID hypothesis, and all these methods exist in this R package, which is called DCOV-PS. So let's see how does this relate to Young box test statistic and how we can actually test the IID hypothesis for a vector value time series.
Sorry,
Based on, yes.
so these are all unconditional, right? So you may think about like generalizing this to sort of conditional, like for example, PACF, partial autocorrelation function.
Yeah, it's not that obvious. Okay, I
Uh-huh.
mean maybe some people have tried, but it's not that obvious. You are right. You are right, but it's not that obvious.
Like moving from conditional moments to unconditional ones, you know, by adding some you know, I think that's quite, there's, you know, people use some weighting to move from conditional to unconditional, right? And then maybe the rest should be the same.
Can you please repeat again? What do you mean from what
So
conditional?
you
What?
have the characteristic function conditional
Yes,
to the past. Let's say if you have
yes, yes,
univariate, so that's the past of
yes.
x, right? Or
Mm-hmm,
intermediate lags, right?
mm-hmm,
And then so I think there is a quite well-established literature that you know, where you can move from conditional characteristic function to the unconditional one
mm-hmm.
by adding some weights like exponential function, etc. I guess you are familiar with that, no? Or
Yeah, maybe. Well, if you are more, well,
yeah, I can
I
send you
need to
some
see what
reference.
you say. Yeah, I need to see what you say. But definitely, of course, it would be nice to have some kind of partial distance covariance.
Hmm.
Some people have tried to do this. Some people have tried to do this, but it is not satisfactory.
So I mean, there is, you know, not using the exact approach as you use this, but there is, like, for example, there's a there is a huge literature on, uh, you know, on as you mentioned at the beginning, on independence using characteristic
Mm-hmm.
function, and they
Yes.
also look at the conditional independence. So this is, if you look, for example, at papers by Albert White and co-authors, so they have a lot of you know, they have a not a lot, I mean, a couple of papers
There are related, okay, there are now you, yes, okay. There are related works with other measures of dependence because this distance covariance
yeah.
actually generated a lot of interest. So there is a martingale difference distance, if I remember right, and they have tried to they try to test actually they do testing of the martingale hypothesis, if this is what you say.
It's more like independence. So and with some application to Granger causality analysis. So it's like you have you look at you look at independence between y and x conditional to z.
Yes, yes.
But z can be the past, for example, of one of the variables, or yeah.
Okay. Well, this would be yes. It's. I mean, okay. I don't want to say something more, but I think it would be nice, to have something like a partial distance covariance. But for me, it's not clear, at least how to generalize it, and
I would be more
to.
than happy to send you some reference.
Okay. Thank you very much.
Maybe there is an easy extension for this, but
Okay.
I will send you these papers. Thank you.
Thank you.
Thanks.
Okay, so yes, back to this question actually, but we didn't use any distribution here. We just used the characteristic function. So anyway, I mean, okay. So let's go back to the generalized spectral density metrics and to see how it can be used. So the standard spectral density approach is becoming appropriate for non-Gaussian cases because, as I said, They miss all these nonlinear processes with zero autocorrelation, the guards, the nonlinear moving average. So the idea is to do this generalized spectral density. So you take these autocovariances, which are if you remember, the covariance between E. I will just show it again if you don't mind. This one, okay? So these are like covariances. And so you take the inverse Fourier transform, so you can write the density. You can write the spectral density because it's like there is stationarity. And then you can put them all together in the matrix. So omega is the frequency. So if your data are IID, then this f function, you see, everything drops down except the value at 0. So the only thing that it has is just a matrix at 0, which has all these elements. So the idea is how to make a test statistic for testing the IID hypothesis. Take the distance of this to this, and try to see what comes out from there. So you can define the kernel estimators. So this is a standard thing that we in time series analysis for the RM element. And then you can define the corresponding matrices and also for F0 under the IID. And then you can take the L2 distance between F hat and F hat 0. So what is the L2 distance? It's just the trace of this conjugate times this matrix. Of course, you need to integrate with respect to omega. So it's just the usual distance, the usual L2 distance. And then when you do this calculation in once, one becomes exactly this thing, okay? So you see, this is exactly the distance covariance, the auto distance covariance of Rm. So choosing here W gives you a range of alternative tools for testing the IID hypothesis. So all this, so if we take this, the weight function by Sykulski and Bakirov, we get this distance. And then we can do a test statistic based on this, because if we take the sum, you see, you have also a sum with respect to RNM, it's the same as this trace. And it can be shown that under the null hypothesis, this is asymptotically normally distributed, and it's a consistent test under the alternative. Let's see how does it work. We study the monthly unemployment rate of the US 4 states. Okay, so we assume it's a 4-dimensional time series. We assume a VAR model, and we just use the usual AIC criteria to get a VAR 5 model for the data. So here is the data, and this is the sample auto distance correlation matrices. So the darker, the more dependence. So we have here so this is lag 1, lag 2, lag 3, lag 4. Each one of these lags are matrices. So you see there is some kind of dependence up to lag 4, and then it becomes grayer. So it means that the dependence reduces. So we fit the model. So there is a residual, as we know, and then we can test for various lag choices. We can actually plot the sample autocorrelation matrix together with this confidence interval. So you see here, so this is a matrix of the residuals, okay? The matrix, the auto distance covariance matrix of the residuals after fitting the model. And as you see, it's quite satisfactory. There are no any problems with, there are no any lines exceeding these blue bars. The blue bars get out of wild bootstrap, as I said, and we can do the testing. And we can use a kernel. We have used the Bartlett kernel for different lags. And this is the multivariate Lung box statistic, and this is our statistic. So we see that we are quite happy, about the results of the test. So the last part that I will talk is about non-parametric clustering of time series. So how can we use this distance covariance, to do clustering? So we all know that the aim of clustering is to partition data into groups where we have some similar characteristics. So now in time series, what does several similar characteristics means? It can be, marginals, it can be pairs, it can be triplets. I mean, the distributions, right? I mean, finite dimensional distributions. So there exist several clustering algorithms. So there is some notion of similarity or dissimilarity. So we want to cluster the component series in a multivariate setup based on energy distance, which is related to distance covariance. The non-parametric methods measure the closeness of joint distribution in terms of their characteristic function. That's the good thing, as we showed before. And it's much, I mean, at least you have less assumptions to make in the non-parametric approach as compared with parametric procedures. So usually what people have done, they do some parametric fitting, or they appeal to second order properties. This is also non-parametric, but they also only appeal to second order properties like autocorrelation function. The closest work to ours is this Zhang and Dan, who consider clustering based on pairwise distribution by copulas. But there are some limitations. So suppose we have a d-dimensional time series. We have n consecutive observations. We want to compute the dissimilarity metrics. And then we will employ the hierarchical clustering. And this is well known and people have used it in applications. So some review about time series clustering. There are just numerous dissimilarity measures. There are many papers, as you see here. And they are all based on autocorrelation, partial autocorrelation, periodogram, spectral density, or the copula. So, and the distance between these form the dissimilarity measure. The thing there is that you can only do it for 2 dimensions. I mean, you can cluster in terms of the bivariate distributions. If you want to cluster for like trivariate distributions, you cannot do it, I mean, with this. Or you can do it, but of course it requires some work. And there are also model-based approaches, like, for example, people assume that there are Riemann Gatz process, and then they do parametric fitting, and then also there are also semi-parametric work. Okay. And then based on these estimators they get for the coefficients, they do some clustering. General dissimilarity measures in time series have been considered early by Kakizawa et al. And Taniguchi and Kakizawa. And these authors have defined a dissimilarity measure of 2 spectral densities in this form, and H is some suitable function. There are many H's that satisfy these requirements, and in the book by Taniguchi and Kakizawa, there are many things. There are many suggestions. So let's see our suggestion based on what we have seen so far. We suppose that y and z denote p-dimensional random vectors, again with characteristic functions phi of y and phi of z. So the energy distance between y and z is just the distance. So here I use mu s because I just get the measure directly from the Sykulski and Rizzo. And of course, we can use, as I said, other measures, okay, like for example, if this is univariate, I mean, even if it is multivariate, we can use the CDF of a normal here. It works. There is a question in the chat. Okay.
No, just
no,
remind.
Yeah. Okay, so let's see. So what is this, the energy distance? How can we express it? So actually, if the first moment exists, then this is finite. And this can be written like this, where the dot means a copy of z and y dot means a copy of y. So this is like centering in some sense, these distances. And this is expression is similar, and there are connections between the maximum mean discrepancy and the distance covariance. There are papers by Grepen and Kostas. So now we have a time series. We want to estimate this. So suppose we have a stationary and ergodic time series, p-dimensional. We denote the stationary distribution by yz, okay? So we have this is the sample. So we can take the empirical characteristic function. So here I put an inner product, okay, just it's okay, and similarly define the empirical characteristic function for z. Then we take the sample, the estimate of this is given by this, and as before, we can write this as a v statistic based on this form. So these are just ordinary distances between y and z, and you can actually calculate very easily, and all this complicated expression can have a very closed form expression, which is nice. So if this let's see what kind of estimator first of all is this. If it is a stationary and ergodic, then if we have first moments, we have a consistent estimator. And in addition, if you have some mixing properties, then you see again, this converts to this. This is a Gaussian process. And it's like a chi-square again here. And if this is not, they don't have the same distribution, then this distance is like asymptotically normal. So there are these theoretical things about times, and all of these proofs are contained in the paper. So how should we use this? How should we use this? The idea is straightforward. So we have data, t-dimensional data. We compute a pairwise dissimilarity matrix using the energy distance. And then we apply a hierarchical clustering algorithm. So this actually can work out, and the dissimilarity measure based on h lag on this. You see the whole process, xtj, xt plus 1j, xt plus 8j, and zt. So again, at the same lags, but at k components. And you can do it for t1 to n, from 1 to n minus h. So actually, we can consider now this vector and this vector, and we can work to calculate the jk, let's say, the similarity between y and z, and we can form the matrix that we want. And then we can use agglomerative hierarchical clustering by using this word linkage algorithm. So there is an algorithm, so we can define this y, this z, then we can have this, and then we can initialize clusters, and we can do, based on the steps of this algorithm, the world's linkage algorithm, we can finally end up with a clustering. Also, you can do clustering by lagged bivariate distributions. Instead of using the h plus 1 dimensional distribution, we can take the lagged bivariate. For example, take L equal 1, you can take xtj and xt plus 1j, and then xtk and xt plus 1k, and so on for different L's. So you can form these distances, and then you can take an overall measure of similarity. So you also do this. You can also do this. It's really, it depends on what you're looking for. Okay? So let's take a simulation to see if this works. So we applied algorithm 1 for different lags, 0, 1, 2, and 5. We actually competed against 15 different measures, or the different methods. As I will show you, the clustering performance with energy distance was the highest with world's linkage, okay? And when the ground, to check the ground truth, there is an index which is defined by this. Okay, this is disputable, of course, but people are using it, especially I have seen it several times in computer science literature. So and maybe there, of course, there are also works in statistics. So there is a ground truth because we have simulations, and A is the clustering. So we can take this sin index between these two. So you see this will be 0 if the clustering is not good, and 1 if the clustering is perfect, okay? So this dot here, this bar here denotes the cardinality of the set. So this is kind of a measure to assess, at least against the ground truth, to assess your simulation. So we have a 40-dimensional time series, and we consider basically we consider 4 independent multivariate time series, each of them 10-dimensional. The first one is a var1 for some matrix B, epsilon t RIID 10-dimensional standard normal. This is var1, the same, but with the errors T2 distributed. Then we have a var2 model with again normal errors as before, and then another var2 model with two degrees of freedom distributed. So here's the comparison of similarity index based on 200 simulations, and this is our method, the first 4 box plots, and the other are box plots that correspond to the results we obtained by applying the other methods. And as you see, for different lags, we are doing very well, even for just by clustering the marginals. So at least we have some evidence that we can go. Of course, the autocorrelation function and the partial autocorrelation function in this case in the periodogram will do well. But I think when you have this this distance covariance, we'll find it better. We'll identify it better. So this is a population of 20 states in the United States. The data example, we have 20, the dimension is 20-dimensional time series, almost 100 observations, and was studied by several authors. And this author, Kalpakis, back in 2000, identified 2 clusters. One set of states had an exponentially increasing trend, while the second set of states had a stabilizing trend. So what we did, we took the raw data, and we calculated the log growth rate for each state. So by this, so PTJ is the population. We recover this the trend-based clustering partially. And okay, of course, our method identifies the difference in the underlying lagged stationary distributions. So this is our result of clustering. And we have these 10 states here, 9, I think, here, and 1. Texas is in the middle. So you see the red states are here, the green are here, and Texas doesn't belong to any cluster. So we have proposed the novel methodology for clustering multivariate time series, non-parametric. I mean, by employing the whole distribution. And the method enjoys good theoretical and empirical properties. And of course, we can consider further things like the case of high-dimensional time series, clustering, non-stationary data, and many others. And this work has been published in the Journal of Time Series. Okay, thank you very much for your invitation. I think I'm done here. Thank you very much.
Thank you very much, Kostas. So I think we have... okay, so there's a question from our analyst, Adam. Adam, yeah, please. Oh, sorry. Do I need to mute you? Yeah.
Hi,
okay.
Kostas. Nice to see you.
Oh, hi, Adam. Nice to see you. How are you?
I'm well, thank you. Thank you for the really great talk. I enjoyed it thoroughly.
Thank you.
I just wanted to start with a remark, if I can, because you mentioned the growing popularity of the auto-distance covariance function, and maybe over time this should just be like rebranded and called like an auto-dependence function. So it sounds more sort of general and than autocovariance, right? Because auto-distance covariance makes it sound more restrictive, but actually it's more general and captures wider forms of dependency. It was just a remark, and I Googled whether auto-dependence function exists, and I sort of found it in one paper, but it's not something anyone's claimed. And I just wonder whether it's a comment that whether it would be, it would sort of rebrand it to something that sounds very general, which it is.
Yeah, I think it's nice, you know. I mean, if we can, yes. I mean, we just use the auto-distance covariance function at that time, you know, because the name was distance covariance, you know, and
Yeah.
this is it. This is it. But you are right. I mean, maybe auto dependence would be better, you know, would be better. You know,
It explains exactly what it does to me, but it's just a remark. My question, if I may, was, you know, so we have this wider generality, and my question is like, there's two parts to my question. The first is at what cost does this generality come? So if we were Gaussian, then we could test by autocovariance for dependency and uni or multivariate. And how much of a loss of power would we have if we go straight to your method? And to ask a harder question with the arch, you know, we could take the squares and do the autocovariance testing on because there's serial dependence in the squares, because we know it's an arch. Would you have a loss of power going straight to yours? And then my follow-up question would be, given your answer to that, what's the right order of attack practically if someone wants to test for auto dependence? Should they first test autocorrelation X, then the squares, then go to your method? Or do you think there's value in just, and also you could get into multiple testing issues if you start doing too much. So that's kind of my question about power versus multiple testing and the right ordering of testing here.
Well, I guess you need first to understand, you need to do some exploratory data analysis to see if you can say something about the marginal of your process. So if there is some evidence about Gaussianity, of course, you can use the autocorrelation function, okay? But for the arts, I'm not sure, I need to check, but I think, okay, you can test in terms of x squared, right? You can test in terms of x squared. I mean, testing what now? The testing whether the first p-values are autocorrelated or test whether the p-values of x squared are autocorrelated. I mean, there is no correlation between the first p-values or you want to test the IID hypothesis. It depends what you want to test, okay? It depends
the latter. The latter, I was thinking we want to test the IID hypothesis. We could either test the squares or we could use your method.
Yeah.
And how would they compare?
I mean, I would, okay, for testing now, the autocorrelation, the testing based on all these test statistics, it's very fast. It's really fast. I mean, it can be done very fast. In the case of our methodology, this is not that fast. It takes some time. It takes some time, and the reason is that because you need to make, you need to finally end up. I mean, to form the estimator, you need to have like you need to be your calculations are of the order of big O n squared, because you need to make a matrix of distances. So necessarily you don't have any other choice. You know, you need. I mean, this is the. So for me, first of all, I would have done some exploratory data analysis, and if I was happy with a GARCH model which has normal errors, you know, then I would have go. I mean, but if with an arch model, but if the tails are different, if the distributions are different, maybe I would have considered the distance covariance. And the distance covariance also can show you, the auto distance covariance function can also show you nonlinear relationship. Maybe it's not a GARCH model, you know, it's something nonlinear. Okay, and you want to test the residuals from this model, you know, whether they are IID or so.
Yeah, nice. So do you think, as a follow-up, that's very clear, and could the auto distance covariance be used as easily? Is the interpretability there to kind of use it as a model building tool?
This
and
is
do
a problem.
Parametric inference.
Yes, this is actually an issue because this function takes a value between 0 and 1, and we don't get any information about the direction of relationship between x and y. Unfortunately, we don't have it. I mean, like we know that if a correlation coefficient is less than 1, then there is negative correlation. If it is greater than 0, it's positive correlation. So we have some information about the direction of the relationship. Unfortunately, this we don't have. I mean, there is not. I mean, at least I'm not aware of something that gives this direction in terms of x and y. So I don't have a real answer to this. You know.
Cool. Okay. Thank you.
I think a follow-up of questions of Adam is, in terms again of identification of the models, I mean, okay, we know this. We have these properties of like ERMA in terms of the values of ACF and PACF. So, for example, ACF can help identify the MA somehow, right?
Yes.
And now, because of because this is quite a a general measure. I mean, in the sense that it can capture linear versus, I mean, linearity and non-linearity. So, if you have something positive, right? I mean, so you see what I mean. So you capture like.
I think this goes back to your previous question. We need a measure of partial dependence, like a partial correlation, to say if something is AR or a moving average.
Yeah, I think that's, yeah.
This goes back to your previous question.
Yeah, this is to complete. I agree, but again, it's like, because your measures are more general, they can capture non-linearity, right? So we can have like your test could tell us that there is an autocorrelation, let's say of order 2, and then maybe 0 after that. But that could be just due to non-linearity, right? And that
yes, exactly.
Yeah.
Unfortunately, yes, I'm not aware of any work that shows the kind of the direction of the relation between X and Y. This is a number between 0 and 1. This is, I mean, this number, to be precise. Well, let's go to the beginning, if you don't mind. This one is a number between 0 and 1. You cannot say nothing more than this, okay? Because this is always positive. It's general. This is always positive, you see? Because it's positive, right? That's it. There's nothing else you can do, I mean.
Yeah. Thank you. So other questions or comments, or we have plenty of time?
So I have one.
Sorry. Yeah.
Can you hear me?
Yes.
Yes. Yeah.
Okay. So thanks, Kostas, for the nice and interesting presentation. And I was wondering about, you mentioned about the computational time of your approach, and also compared to the fact that if you want also confidence interval, as I've seen, you compute it with wild bootstrap. So I was wondering if one wants to speed up a computation, especially for the confidence interval, do you think that maybe the asymptotic distribution can be somehow used to construct?
Maybe, yeah, it would be nice, I mean, if there is a yes, but as you see, it's very complicated, right? I mean, definitely, let's say I didn't give the distribution here. There are results also for the both for the univariate and the multivariate case. This is a bit different for the distance. So you need somehow, to know how to simulate this integral, okay?